Hello everybody and welcome to the beginning of section 1.6 on page 31 of the workbook. And the topic of this section is the second derivative, a new concept for us. Okay, and I think the best way to just introduce this concept, get a feel for what this is about, is to start with a conceptual example. Okay, so let's take a minute just to read through this together. So they're giving us a rabbit population P in hundreds of rabbits, and it's described in terms of the function P equals f of t, and they give us a graph of that function over here to the right, okay, where t is measured in years. We'd like to do some estimates based on that graph. Okay, so how about if we start out by just looking at the units that we're talking about on our axes. So on the horizontal axis, we've got t. They're telling us that that's being measured in years. And then population P is in hundreds of rabbits. I'll just abbreviate that by writing hundreds here. Okay, and all of these questions are going to be conceptual questions involving behavior of this function. Okay, so starting with A here. So it asks us on what intervals, and what they mean is intervals of time, is the rabbit population increasing. So as you look at that graph, okay, where is the rabbit population increasing? Well, the thing is, the graph is going up left to right for the entire interval, so it's actually increasing everywhere from t equals 0 to t equals 10. Okay, so let's write that down in words. Okay, on the interval 0 less than or equal to t less than or equal to 10 years. That's the entire time interval that we're talking about for our graph. Okay. And then what about B? On what intervals, if any, is the rabbit population decreasing? Well, we kind of mentioned in part A that the population is increasing everywhere, so that means it's not ever decreasing. Okay, so never decreasing because our graph never goes down left to right. Is never decreasing. Okay, and then we come to C and D, and they ask questions that are a little bit more challenging to think about. Let's look at C here. So now they're asking us on what time intervals, if any, is the rate of growth of the rabbit population increasing. Okay, so now they're not asking us about the population directly, they're asking us about its rate of growth. How do we look at the graph and determine where the rate of growth is increasing? Okay, well remember that the rate of growth is about the slope. So it's kind of graphically asking you, where is the slope of this graph increasing? Okay, well, let's draw in a few tangent lines, okay, because those will give us an idea of the slope. And notice that starting at 0, it looks like the slopes are increasing. That's telling us that the rate of growth of the population is getting bigger. The question is, how long does that keep up? Okay, so how far to the right can we go and still have this property that the tangent line slopes are going to keep increasing? If you think about it a little bit, I would say that the cutoff is maybe somewhere in the vicinity of 5. Okay, after 5, the tangent line slopes would start decreasing, so it looks like 0 to 5 years is the interval that we're looking for. Growth rate is increasing on the time interval 0 less than or equal to t less than or equal to 5 years. Okay, and we could maybe mention how we made that observation because the slopes of the tangent lines are increasing. Okay. And so now that we've answered C, let's see if we can answer D. It's just turning it around and saying, on what intervals is the rate of growth of the rabbit population decreasing? Again, rate of growth graphically is slope. And notice that if we start drawing in tangent lines between 5 and 10, we kind of get the opposite behavior. So here's our tangent line slope at 5. And now, if you keep drawing in tangent lines, notice that those slopes are getting less steep. They're numerically decreasing. So even though the slopes are positive everywhere, the magnitude or the slopes themselves are getting smaller. Okay, and so we could say that the rate of growth of the rabbit population is decreasing between 5 and 10 because of those decreasing slopes. The slope of the graph is decreasing on this interval. Okay, and one just little issue of notation technically, and this isn't terribly important, but I should write less than and not less than or equal to, just so that we don't have overlap between our answers in C and D. Okay, so I'm going to fix that. All right. Now, I think we've answered the questions that they asked us. I do want to make one comment about notation. Okay, this may come up later in this section, so just to make you aware of it. There is an alternate notation for intervals. Okay, so I'm going to be looking back up here at part A for a minute. So this interval from 0 to 10. Okay, you can write that down using kind of a shorthand notation. I want to just add that here. So if I use the phrase the interval, and actually, I think it would be better to illustrate this point. I'm going to pick one of the open intervals down here. Okay, sorry about that. I want to illustrate this point with this interval instead in part C. Okay, so zero less than t less than 5. Okay, can also be written like this. Zero, 5. Okay, in other words, what I'm saying here is that instead of writing this, 0 less than t less than 5, sometimes you'll see books write this. Okay, it's a little confusing because when you see 0, 5, you think that looks like a point 0.05, but in this context, it represents an interval. Okay, so just be aware that if you see that notation in the context of talking about intervals, we're really saying all t values between 0 and 5 when we use that notation. Okay, we'll see some other examples of that later in this section.